Among the 6 flavors of quarks, one stands out as particularly unusual, the strange quark. Its name reflects the sense of surprise and mystery it inspired when first discovered, and its properties continue to intrigue physicists today. Unlike the up and down quarks that dominate ordinary matter, the strange quark is heavier, more exotic, and appears mainly in particles that exist only briefly or under extreme conditions. Despite its relative rarity in the everyday world, the strange quark plays a pivotal role in understanding the underlying symmetries and subtleties of the subatomic universe. The strange quark is essential in forming particles called kaons, hyperons, and other mesons that were first observed in cosmic rays and particle accelerators. These particles behave in ways that seem counterintuitive, decaying in patterns that violate certain symmetries, a phenomenon known as CP violation. The study of these decays helped scientists unravel fundamental questions about the imbalance between matter and antimatter in the universe. Without the strange quark, much of the insight into why the universe is dominated by matter rather than being a mirror image filled equally with antimatter might have remained hidden. Strange quarks exist in a dynamic dance with gluons and other quarks. They are never found alone, as confinement binds them into composite particles. Inside a kaon, for example, a strange quark pairs with an up or down antiquark, held together by the unrelenting pull of the strong force. The gluons that mediate this force interact with themselves as well as the quarks, creating a constantly shifting, energetic field. This intricate web of interactions generates the mass, charge, and decay properties of the particle, and it reveals the deep and subtle architecture of the quantum world. In extreme environments, such as the cores of neutron stars or the conditions created in high-energy particle colliders, strange quarks become even more significant. At incredibly high densities, matter may exist in a form known as strange matter, where strange quarks are no longer confined to individual particles but exist in a dense soup, potentially stabilizing exotic stellar objects. Understanding the strange quark is therefore not just a curiosity of particle physics, it has implications for astrophysics, cosmology, and the behavior of matter under extreme conditions that cannot be replicated naturally on Earth. The strange quark also highlights the richness of quantum chromodynamics, the theory that governs the strong force. Its interactions reveal the nonlinear, self-interacting nature of gluons and the delicate balances that hold quarks together. Studying the strange quark allows scientists to test predictions of the Standard Model and to probe anomalies that might hint at new physics. Its fleeting presence in mesons and baryons provides a laboratory for exploring the very rules that govern the quantum realm. Offering insights into forces, symmetries, and the mechanisms that sustain the universe, the very existence of the strange quark challenges classical intuition. It demonstrates that the universe is not limited to the simple particles that dominate our visible world, but includes a rich spectrum of constituents with properties that defy expectation. The strange quark embodies the idea that nature's rules are intricate, subtle, and often surprising, and that even a particle that seems exotic or peripheral can have a profound impact on the behavior of matter and the structure of the cosmos. In high-energy experiments, strange quarks appear and vanish in moments, producing mesons that decay and transform, leaving traces for scientists to reconstruct their brief lives. These observations allow us to explore the hidden symmetries and violations in nature, to understand the hierarchy of particle masses, and to study the mechanisms that gave rise to the universe as we know it. The strange quark's fleeting existence is paradoxically permanent in its influence, shaping the processes that underpin the stability of matter, the evolution of stars, and even the dominance of matter over antimatter. To contemplate the strange quark is to contemplate the universe's elegance and mystery. It shows us that even the smallest, most fleeting components of matter carry enormous significance, linking the ephemeral to the enduring. Strange quarks connect the physics of subatomic particles to the structure of exotic stars, the patterns of particle decay, and the ultimate questions of why our universe exists in its present form. They remind us that the hidden world of the subatomic is not only complex but also profoundly beautiful, revealing a cosmos where every particle, even one as elusive as the strange quark, plays a role in the grand architecture of reality. In essence, the strange quark is a gateway to understanding the extraordinary richness of the quantum world. It is a particle that challenges intuition, exposes hidden symmetries, and connects the ephemeral microcosm to the vast expanse of the cosmos. Through it, we see that the universe is not merely composed of what is familiar and visible but is woven from layers of subtle, intricate, and astonishingly strange elements that define reality at its most fundamental level.